Okay, any questions before we start? If you remember, we are considering basically the effect of the quantum mechanical properties of interaction with electromagnetic fields. Now, there is some new quantum mechanical phenomena in which, for example, in places where the magnetic field is zero and the electric field is zero, in classical physics, the particle doesn't feel any force. So if the particle cannot enter the region where there is a non-zero magnetic field, the particle will just not feel it. So it is as if there is no magnetic field anywhere. But what happens in quantum mechanics is the Schrödinger equation depends on the vector potential, not the magnetic field. And even if the magnetic field is zero, it doesn't necessarily mean that the vector potential is zero. And we had seen some examples, if you remember this, particle confined in a cylindrical box where inside the box there is no magnetic field, but the magnetic field is just penetrates through the cavity inside the box. And the particle doesn't feel the magnetic field. Nevertheless, the energy levels, the quantum energy levels, do feel the effect of the magnetic field, although it doesn't go through. But then there's still the problems, like the vector potential is not unique. So we basically have infinitely many vector potentials and the scalar potentials that correspond to the same electric and magnetic fields. Classically speaking, we can use any one of these and they should be basically describing the same, exactly the same physics. Now this is still said, although we see some effects that depend on the vector potential, and those effects basically still are gauge invariant, meaning that whichever vector potential you use, you obtain exactly the same effect. This is basically reflected in the fact that, for example, when we were describing the energy levels basically depended on if you remember the radial equation depended only on the total magnetic flux, not on the vector potential. It feels the vector potential, the effect of the vector potential, because it never enters the region with a magnetic field. Nevertheless, the effects that the vector potential cause are still related with the magnetic field, which is gauge invariant. Now, today we will be basically discussing another phenomena, the Aharonov-Bohm effect. Well, last week, in just 5 minutes, I just sketched what we will be doing. I will be mainly doing it in some more detail today. Now, the basic idea is we will use the path integral formalism because the Aharonov-Bohm effect in the path integral formalism will be almost trivial. And this is another observable effect of the vector potential. So we still have particles. We will be considering this problem. We still have a region where the magnetic field is non-zero. Outside, the magnetic field is zero. And we will assume that the particles cannot penetrate into this region of non-zero magnetic field. It's kind of confined. You can just imagine that you have a solenoid which doesn't allow your particle to enter the solenoid. So classically, the particle will never feel the effect of the magnetic field, but nevertheless, quantum mechanically, we still see the effect. We will see the effect. And we will be looking at the double slit experiment. So let's say we have these double slits, two slits. And we have some kind of a source over here. We are sending, you can say that we are sending electrons, for example, or any kind of charged particles. And as they are propagating, we know from basic quantum mechanics that the wave function, the amplitude of propagation will be the sum of the amplitude that the particle will go from the top slit plus the amplitude that the particle will go from the bottom slit. So the total amplitude, let's say this is x0, this is x1, the total amplitude that the particle starting at x0 at the time t1 goes to the point x0 at t0 goes to the point x1 at t1. Basically, in the path integral formalism, we can just write this as e to the power I over h bar the action. and we are summing over all possible paths. Now, we will be basically dividing these paths into two classes. We will have, well, in reality, in fact, we will have infinitely many classes. So we will just split them, consider the two cases, d of xt. Let me call these points C and D. E to power I over h bar s of x. The path goes through the point C, the slit C. So that's basically, I'm summing over all possible paths, and I'm dividing all paths into two parts. The paths that go through C plus the path that go through D. Well, there is a simplification over here. You see, in this path integral, we are not really restricted by anything. So whichever path you can imagine, it contributes to the sum. So there are paths that, for example, the particle starts from x0. It goes through slit C, then slit D. It goes through C and then back from C, and then again through C and goes to x1. So there are such paths that will contribute to the path integral. But I'm basically ignoring such paths. Because basically what happens is, just if you consider h bar to be a small parameter, the main contribution will be from possible classical paths or paths that are close to the classical paths. So the path that starts from x0 goes through C and then reaches D in a more or less straightforward fashion will contribute more than such a hypothetical red path. The red path, the contribution will be most of the time negligible. Just a warning, I think it was just a couple of months ago, I don't remember the date now, there was an experiment which actually measured the effects of such paths. The effects of paths that start from D goes to C and then back again through D. So these effects are measured. It was just, as I said, just a couple of months ago. So what they did was they basically created a tube connecting the D to C. And they had seen some changes in the interference pattern. So I will try to find the reference for you. But for this argument, I will just ignore those things. Now this S is nothing but the integral of the Lagrangian from the time t0 up to t1. Now we had seen that the Hamiltonian of our new system can be written as P minus Q over C A squared over 2m. If you want, starting from this Hamiltonian, you can obtain the Lagrangian. Lagrangian has a much simpler form. Lagrangian just has L0 plus Q over C A dx by dt, where L0 is the Lagrangian in the absence of A. So just to add the effects of a magnetic field, you just add that term to the Lagrangian. It's kind of a velocity-dependent potential. Now, the thing is, the action can be written in this form. It's the integral of dt which is the integral of L0 plus Q over C A dot dx by dt. Well, the first term is just the action in the absence of the vector potential, plus the second one, Q over C A dot dx by dt times dt. Well, kind of you can just cancel the dt's and you obtain an integral not over the time but over the path of the particle, as the particle goes from the point x0 to the point x1. Now let us just imagine two particles, two paths. Such a path, this is, let's say, path 1, and then this path, path 2, starting from x0 up to x1. And this is just arbitrary path. I'm not paying attention to whether they are passing through the slits or not for the time being. Now the integral from x0 up to x1 through path 1, a dot dx, minus the integral from x0 to x1 through path 2, a dot dx. So I'm just looking at how my integral changes if I change my path. Well, this will be equal to, from x0 up to x1, a dot dx, plus x1 to x0, a dot dx. This is through path 1, this is through path 2. I'm just changing the limits of the integration. When I change the limits of the integration just gets a minus sign, so that it makes a plus. Well, you see, you go from x0 to x1 through path 1. This is the first integral. In the second integral, you go from x1 to x0 through path 2. I'm just looking at the difference. You see, this is not a path integral. This is a line integral. I'm just looking at how my line integral changes as I change my path. Does it change? Does it stay constant? When does it change? That's what I would like to study. So I'm just looking at their difference. If the difference is 0, it means that if I change my path, nothing changes. But if I look at the difference, then what I obtain is nothing but a closed integral of A over the closed path, as I go from 1, then back from 2. But this closed path integral, I can write it as the surface integral of the curl of A. But the curl of A is just B. So this is the difference with change in my line integral as I change my path. Now you see, in this problem I didn't yet really specify any B field yet. I will be applying this result to my study of the Aharonov-Bohm effect. But what we can say over here, you see, if there is no magnetic field between these two paths, then the B will be 0 between the paths. So the integral of B over that area will be 0. So the result of my integration does not change. If there is a magnetic field, of course, the result will be different. Let's look at my example now over here. Now, basically, I will be assuming, again, make another assumption that this region of B field is sufficiently small and sufficiently behind the screen so that the paths I have this form. For example, when I consider paths that go above that go through the C slit, most of the contribution to my integration will have such a form. Will look like this. These paths will give me the dominant contribution. But between those paths, there is no region which has a magnetic field. So when I'm summing over in this path integral, when I'm summing over paths that goes through the slit C, at least the paths that contribute, they have the same integral of A over the path. So this is what I will do. So this is my one path integral. Well, the same argument you can use if your path goes through the slit D. This is equal to sum over paths that goes through slit C or D of the action in the absence of the magnetic field plus I over H bar Q over C A dot dl. But for all those paths that goes through C or D, this line integral is the same. The integral of A dot dl is the same for all of them. So I am summing over all paths which contain the same factor. So I can just factor out that common factor. So this will be equal to the x of t e to power I over h bar s0 goes through the, still I'm summing over the paths that go through slit C or D times e to power I over h bar q over c line integral of A dot dl. And when I'm evaluating this line integral, I take a path that goes through slit C. I don't really care which path you take because all the paths basically give the same result as long as it goes through the slit C. Now let me just call this the amplitude x0, t0 up to x1, t1, c or d, 0, e to power I over h bar q over c A dot dl through slit C or D. So that is the first path integral is nothing but the amplitude that the particle starts from x0, goes through the slit C or D, and then reaches the point x1. Now my total amplitude will be equal to, well, the amplitude that it goes through C in the absence of any vector potential multiplied by that exponential I over h bar q over c integral of A dot dl. This line goes through slit C plus the amplitude that my particle goes to x1 from x0 through the slit D and the amplitude of exponential of I over h bar q over c a dot dl, but this time this path goes through slit D. Plus, this is equal to, let me just factor out a common phase. x0, t0, x1, t1 through C in the absence of any vector potential, plus the amplitude that it goes from x0 to x1 through the slit D, again in the absence of any vector potential through D, times the exponential of I over h bar q over c a dot dl through slit D minus a dot dl through slit C. I just factored out the common phase. Well, you see, this is my amplitude that the particle will go from x0 to x1. Now, what I will observe, in the double slit experiment, what we observe will be an interference pattern. And this interference pattern, if you look at this expression, well, in the absence of the vector potential, this term over here would be absent. And then you would get whatever interference pattern you will get. But once you turn on the vector potential, that is, turn on the magnetic field, if you put a magnetic field in just behind the slits, such that classically the particle has no way of reaching there, even quantum mechanically you can make sure that the particle can never reach there, you see that there is this term, which you should add. And that term just changes the phase between the two amplitudes. The amplitude that the particle goes through C or the particle that goes through the slit D. And hence the interference pattern will be different. Now you see that interference pattern, that phase difference between the interference pattern, you can just write it as the exponential of I over h bar q over c, just the magnetic flux.
Hocam bir şey soracağım. Hocam bu manyetik flux'ı biz mi yaratıyoruz? Yani sistemde var olan bu manyetik flux'ı yoksa bu line integrallerin oluşturduğu bir şey.
You see, this is our setup. Just imagine this case. You have this double slit. You have this double slits. You create these double slits. Behind the double slits, you put some kind of a cylinder, let's say, a very long cylinder, and you send electrons, let's say. Okay. Now, within this very long cylinder, at first you don't do anything. You just send your electrons. The electrons will not be able to penetrate into your cylinder. And at the end, you get an interference pattern at the other side of the screen. So this is your first observation. Then what you do is, inside this cylinder, you put a solenoid. So that inside this cylinder, you create a magnetic field. But I repeat, your particles cannot enter that region. So classically, there is no way whether you put, if the particles were just behaving classically, the particles wouldn't know whether there's a magnetic field inside your cylinder or not. But you just go and put a solenoid there. And what happens is, when you put a solenoid there, creating a magnetic field, you are creating the magnetic field. You turn on the current, let's say, in your solenoid, you see that your interference pattern starts shifting. Now again, classically, your particles never feel the magnetic field. So classically, nothing should be changing. But what happens quantum mechanically is your particles feel the vector potential, feel the existence of the vector potential. And hence, you end up seeing observable differences. What will happen is your interference pattern will be shifting up or down depending on your magnetic field, on the direction of your magnetic field. So this is something that you can actually observe. Although the particles never feel the magnetic field, you will be able to tell whether there is a magnetic field in the region or not. And again, if you notice over here, although the effect is due to the non-zero vector potential in regions where your particle moves, the final effect is proportional not to the vector potential, but rather through the depends on the vector potential through the magnetic flux or the magnetic field. So although you can choose different vector potentials corresponding to the same magnetic field, all of them will give you exactly the same result.
You said that if you put the cylinder behind the screen, what will happen if you put the cylinder in front of?
Well, you see,
It will be already inside the console.
well, you see, there are a few things that we had done, a few assumptions we had done. So one thing we are saying that, okay, the particles cannot feel the magnetic field. This is just an idealization. In a realistic case, there will always be some finite possibility that the particle will be able to penetrate through, will be tunneled through your whatever barrier you put over there. So by putting it behind the screen, what we are doing is actually reducing that probability. You see, for the particle to be able to reach that magnetic field behind the screen, what kind of a path it should have? It should start from x0, goes through C, and it should take such a path. Do you see it? Yes. If you imagine such a path, well, this path goes through the region which contains the magnetic field. But you see, if you look at this path, ideally you should even put this region very close to the barrier. Well, it should deviate significantly from any classical path. Yeah, that will be kind of tough. Well, if you put it in front of the screen, well, maybe you have a particle that starts, there are some other effects you ignored that causes the particle which starts to move in one direction, then that other effects that you didn't take into account kicked it into the region of the magnetic field, and then it goes through the slit C. Our derivation over here will be the same whether you put it behind the screen or behind that barrier or in front of the barrier, nothing changes. But the validity of the approximations we made will be modified. Yes, it's not so easy to create, if you want to do experiments with electrons especially, it won't be. If you want to do an experiment with electrons and you want to have measurable interference patterns, if you want to realistically realize such a case, it's not easy to create a region where the electron cannot penetrate. Because the slits should be close by. Well, how do you create a very small solenoid? In practical applications, what they do is they put some kind of a magnetized object over there. But the magnetized object, the electron can still go through there. So, I mean, this derivation over here you won't be able to test this exactly, but this will be just an approximation to what you should observe. Well, there's an interesting thing though. You see, this is just a pure phase. If Q over H bar C times phi B, let me put 0 over here. Let me not. Phi B is some multiple of 2 pi. Or phi B is equal to n times phi B0, where I defined phi B0 as 2 pi H bar C over Q. It can be positive or negative. You don't see anything. There will be absolutely no effect. And this number over here, for an electron, is 4 times 10 to the power minus 7 Gauss centimeters squared. Well, it's a small number, but basically that's called the fundamental unit of the magnetic field, magnetic flux. For example, is anyone of you interested in superconductors? Okay, you have probably heard of what superconductors are. There are basically 2 types, type 1 and type 2. And the difference between type 1 and type 2 superconductors is that type 1 superconductor doesn't allow any magnetic field inside. So if you push magnetic field strong enough into your superconductor, it just loses all its property of superconductivity. But if you have a type 2 superconductor, if you try to force some magnetic field to go through it, what happens is you create some regions, some tubes inside your superconductor, which is non-superconducting. Nevertheless, outside these tubes, you still have regions of superconductors. So basically, if you have a superconductor, and this is a superconductor, and when you force a magnetic field through your superconductor, type 2, well, the field lines will go through the superconductor, through certain regions. So these regions over here, these tubes, let's say, are non-superconducting. Now the flux, well, there's some magnetic field going through the superconductor. The flux going through them is just phi 0, this fundamental unit. Of course, the Q over there should be the charges inside the charges that are moving inside your superconductor. And it turns out that the charges inside the superconductor has a Q is equal to twice the electron charge. Twice the electron charge, because we know that the phenomena responsible for superconductivity, although we don't have a full theory of type 2 superconductivity yet, it's basically the Cooper pairs. So it's the electron pairs that create somehow this superconductivity. So that's why we have twice the electron charge over there. Any questions? Okay, let's give a 10-minute break now then. In the second hour, we will be discussing magnetic monopoles. So if any one of you is interested in high energy physics, one of the searches is search for magnetic monopole, which classical electrodynamics tells us that it doesn't exist. Now, although there are no experimental hints for existence of magnetic monopoles, there is one indirect hint that a magnetic monopole should exist, is that charge is quantized. We know that charge always comes, if you just call the fundamental unit of charge as 1/3 the charge of the proton, for example, all the charges we observe are just integer multiples of 1/3 the charge of the proton. There are no particles, whether fundamental or composite or complicated, no matter how complicated structure it might have, no particle has, for example, 0.7 times the charge of the proton. It just doesn't exist, and we don't know why. But if there is a magnetic monopole, a single one is enough for us. If there is a single magnetic monopole, then it tells us why it should be so. So in a sense, you can say that the discreteness of electric charge is basically an indication that the monopoles should exist, and hence we are looking for it. Okay, we will discuss it in the next hour.